like really sleepy. I can go? Okay. Hi, everyone. Today I'm here to talk to you about how algorithms can improve your life. So we've learned in our program about, oops, sorry. I am not in the right place. It's not changing, Chris. Never mind. Okay. So we've learned about how algorithms are step-by-step processes that can help us solve problems. Oh, you guys get the joke, okay. And this is really important in computer science because in computer science, you come across a lot of problems related to trade-offs. And today I'm going to talk about 3 kinds of trade-offs. The first one is the trade-off between sorting and searching. So the relationship between sorting and searching is basically why do we even sort in the first place, right? Primarily, we sort to minimize the pain of searching in the future, which brings up the question, are you even going to search in the first place, right? And if you are, how often are you going to search and how detailed does that search have to be? The idea behind this trade-off is whenever possible, you want to embrace as much mess as you can tolerate. And the reason for this is that if, let's say, you search through something that you haven't sorted, at worst, you waste a little bit of your time. But if you spend a lot of time doing a very detailed sort and you wind up never searching through that at all, then that's a huge waste of time. Let's say it comes down to that you actually do encounter a situation in which you have to sort. Is there an algorithm that best accomplishes that? And it turns out that we did learn about an algorithm called merge sort. This sort has been dubbed by some computer scientists as legendary in the history of computer science, primarily because it accomplishes these sorts in linear rhythmic time. So we probably learned it more as n log n. The other advantage of merge sort is that because of the splitting that happens near the beginning, it easily adapts to parallel sorting. Now you might be wondering, okay, linear rhythmic time, that's not bad, but is it possible to do even better? Can you do a sort in possibly linear time? And the answer is yes, you can, with a couple big caveats. There's something called the bucket sort, which I don't think that we covered in our class. But the 2 caveats are, 1, you aren't so concerned about a precise head-to-head comparison between the items that you're searching, and 2, that you're able to design categories such that there's an even distribution among the buckets for the things that you're sorting. If you are able to accomplish these 2 things, then you are able to achieve a sort in linear time. So there is that. So the next thing, the next trade-off I'll talk about is explore versus exploit. Now, in computer science, exploit doesn't have quite the big negative connotation that it has in everyday language. Exploit, in this case, just means that you're able to capitalize and garner some rewards based on information that you've gathered during your exploration phase. So, the classic example that demonstrates this tension between explore versus exploit is something known as the Multi-Armed Bandit. It's called the Multi-Armed Bandit because it involves a slot machine. A slot machine is sometimes called a single-armed bandit. And today I'm going to talk to you about a super simple example of a multi-armed bandit involving 2 slot machines. So the first slot machine, let's say we've played a total of 15 times. We've won 9 out of those times for a win rate of 60%. And the second slot machine, we've only played twice, and we won once, so that our win rate is 50%. Now the big money question is, which of these 2 machines should you play? And the answer is, not surprisingly, it depends, right? That's always the answer to all of life's deepest questions. But here, it specifically depends on how long you intend to play. Now that brings up a very important consideration when you're deciding whether to explore or exploit, and that is the time interval. Where along that time spectrum are you? Because if you are earlier in the spectrum, you are better off exploring. You want to go out there, you want to gather data, in the possibility that you might find new favorites, new great things. However, if you're further along that time spectrum, you're probably better off exploiting, because by this time you've probably gathered the favorites that you like, and it's a good idea to fall back on those reliable things. All right, so let's say that you're in your exploratory phase and you are wondering, well, still, which of these slot machines should you choose to play? So there is an algorithm for that. It is called, well, there are many algorithms, but this is one of them. This is called the upper confidence bound algorithm. There are different versions of it. And the reason that this algorithm is so great is it does a fantastic job of minimizing risk. And they've done a lot of work, they've done a lot of math, did a lot of research, and this graph demonstrates how good the UCB algorithm is at minimizing risk. You can see here there are several algorithms modeling that bandit problem that we are looking at, and you can see that the bottom two, which are different versions of the UCB algorithm, do the best at minimizing risk. So how do you put it into practice? So if we can imagine that in this scatter plot, each of these dots represents a slot machine, then according to the UCB algorithm, the slot machines that you want to choose are the ones with the higher upper bounds. Now this is interesting because you'll notice that these slot machines, although they have higher upper bounds, they also have greater uncertainty, right? And you could tell that because of the longer vertical lines. And you'll notice that the expected value of these slot machines are actually lower than something like this over here, right? That dot is higher, right? So you, in fact, it's more reliable and it's higher. And yet UCB still encourages us to explore in our exploratory phase, to choose the things with higher uncertainty because it's so early on that you don't know, right? Maybe it's kind of like that second slot machine. You've only played it twice. You don't know. Maybe it might be turn out to be a big winner in the end. For this reason, a lot of people describe the UCB algorithm as an optimistic algorithm because it's less concerned with past performance and more concerned with the best possible performance in the future. So this is great, right? Because that means for us, when we go out there, whether we travel to a new place or move to a new city, at the beginning, it encourages us to go out there and explore new things, meet new people. And yet, you know, towards the end where we're settled in and we're drawing near to our time, maybe we're going to leave the city, it's better to fall back on the things that we've grown to know and love. And finally, the last thing I'm going to talk about is the look versus leap trade-off. So the look versus leap trade-off comes up in something called the optimal stopping problem. You come across this situation when you have to make a decision. We do this all the time when it's lunchtime and we're wondering where we're going to go eat. So we have all these choices and we want to know, well, what should we choose? And oftentimes the question that's asked is, which one is the best choice, right? But really the better question is, how many choices should we consider before we stop that search? So one of the algorithms to help us make in this decision-making process is the look then leap rule. The idea here is to divide your search into two separate phases, the look phase and the leap phase. And in the look phase, what you're going to do is ahead of time, you're going to set forth either how many options you're going to consider or how much time you're going to spend on this problem. And in the leap phase, that's when you're actually going to make your decision. Now, this is a little bit vague, so I think it might help to consider an example. So let's say that we want a puppy, right? But we only have limited time to choose a puppy. So we've decided, okay, well, we're going to look at maybe one puppy every day for maybe a little bit more than a week. And so we've got 8 puppies. The question is, at what point will we stop the look phase and transition into the leap phase? So they've done a lot of work on that, and they've come up with a number. And that number is 37%. Generally speaking, so in this case, 37% 37% of the dogs is the first 3 dogs. And so what we would do is we'd look at each of those 3 dogs, not choosing any of them, no matter how cute and adorable they are. And then after that, we're going to consider the next 5 dogs, one at a time, no backsies. And the first dog that we come across that we love more than all the other dogs that we've seen, that is the dog that we choose. I know, it's a smile. How can you not love that? Now, there's a downside to doing this method, which is that we actually never get to look at the last dog, right? And this brings up a problem with the 37% rule, which is that it actually only works 37% of the time. And there are a couple reasons for this. One is that in the first situation, maybe the best option happened during the look phase. Or it could be like the last option where the best choice was actually too far deep into the group, so you never actually got to consider it. So you might be wondering, well, 37%, I mean, that doesn't seem so great. In our puppy situation, 37% is actually not bad, because if we had chosen a puppy at random, 1 out of 8, that works out to 12.5%, so 37% is pretty good. But there is an option that is better. That's the threshold rule. In the threshold rule, the big difference is that we have information. Previously, when we were looking at these puppies one by one, we don't know what the next puppy is going to be like. But here, this would be the situation in which we have all the puppies, right? And let's say that we had some cuteness measure, right? So that we know what the average cuteness is of this group of puppies. And then each puppy, we get to know what its individual cuteness score is. And then we can use that to gauge, like, at this point, am I going to choose this puppy or the next puppy? If you follow the threshold rule, you have a much better chance of picking the best choice. You have a 58% chance. And the last slide. So all of this ties back to how do we apply the threshold rule in our lives. All of us are going to embark on job searches soon. And a good example of a threshold that we could use is something called the reservation wage. So for the reservation wage, if we get offered a job that's above this point, where it's a good idea to accept it. But if it's below this point, it's a good idea to reject it. Now, when you look at these formulas online for the reservation wage, it's actually super complicated with a lot of Greek letters and infinity symbols. But on Wikipedia, there is it's something that you could use to sort of model what you're going for. This is an equation for when is a good time to sell your house. And you can see that it depends on some familiar factors, right? Like, what is the amount of the offer? How much time has passed? And what is your cost in passing up that offer? So these are some things that we could consider when we go out there to field these job offers and figure out, like, when is a good point to stop searching. And that's pretty much it. These are my references. Pretty much everything I talked about today came from this book called Algorithms to Live By, which I heard about from this podcast called Note to Self. And of course, there's the obligatory Google and Wikipedia. So, thank you.